Look at practice question set number 11 here, all 9 of those questions. Following diagrams show 2-point sources and selected field lines. The solid field lines result from determining the direction of the net electric force on a test charge placed at a point in the line. In other words, those solid ones are the electric field lines. Does that make sense? Okay, it's representing the force on a charged particle in between there. Okay, those are electric field lines. And notice those have arrows on the end of them. These other lines, these dashed lines, they tell us that they represent, or they result from connecting those points on a plane that have the same electric potential or voltage when a test charge is placed at that point. So in other words, if you put a little charge right there, it would experience the same voltage as if you put the charge right there or right there. Similarly, the potential there would be the same as the potential there and there. We call those equipotential lines. You don't have to know about equipotential lines in Physics 30. Okay, that's not the point of this question. The point of this question is the difference between a vector and a scalar field. The field represented by the solid lines classified as a vector field. You know that because there's arrows on the end of it, right? The field represented by the dashed lines is classified as a scalar field because there's no arrows on the end of those lines. That's all that they expect you to know there, right? The difference between a vector and a scalar. Numeric response number 1. The electric field strength, 4 centimeters from a 1.2 times 10 to the negative 5 Coulomb point charge is what? Got centimeters there. Is this a producer or experiencer? Sometimes it's helpful to draw that diagram, right, to determine whether it's a producer or experiencer. So let's say here's my charge, 1.2, it's positive 1.2 times 10 to the negative 5. We're trying to find the field strength a certain distance, 4.00 centimeters away from it. Can this 1.2 times 10 to the negative 5 Coulomb charge experience the field over here? No, it can only experience it if it's there. If you're trying to determine what the field is right there, then the charge, if a charge is experiencing that field right there, then it has to be right there. And this charge, 1.2 times 10 to the negative 5, isn't. That means it must be a producer. We're going to use the equation E is equal to KQ over R squared. Okay, we got the charge there. So make sure you make R 0.04 meters and make sure you square it. When you do that, you should get 6.74 times 10 to the 7. We could say newtons per coulomb as they have here. What's our new set of units that we can use for electric field? Volts per meter. Newtons per coulomb or volts per meter. Either one of those would be okay there. 6747. Multiple choice number 2. When I read this, I'll be honest with you, something else jumps out at me beyond what we have to do in this question. Okay, this question says, what's the electric field between the top and the bottom grids? And we can do that, right, using my uniform field equation, my uniform field producer equation, delta V over delta D. It's a pretty straightforward question, actually. The potential difference is 1.20 times 10 to the 2. We're giving that number up in the diagram, and the distance is 4, so that makes my electric field 30.0 newtons per coulomb. And what is it, up or down? Field is down. Who said down? How do you know it's down, Nick? Yeah, the field always goes away from the positive, and the field always goes toward the negative. Make sense? All right, so what else do you think jumped out at me here? What else do you think that when I read this question, I'm thinking we're going to end up having to do here? Yeah. Like I see this is collision, right? We got some velocities there. Like as soon as I read that, I'm thinking this is conservation of momentum, right? And then I wasn't asked anything about that, but you could see how a scenario like this could be used for a couple of different things, right? An electric field thing and then something that's completely different like conservation of momentum. All right, next question. A pair of parallel plates is separated by a distance of 1 centimeter connected to a 12-volt battery. The magnitude of the electric field is E. The second pair of plates, identical to the first, is separated by a distance of 3 centimeters and is connected to a 6-volt battery. Those volts, by the way, represent what? 12 volts and 6 volts represent what variable? Delta V, the potential difference. That's the difference in energy per coulomb of charge between two plates. So the potential, the electric potential, or the energy per coulomb of charge at this plate is a certain value. At this plate, it's a different value, and the difference in potential between those two plates, or the difference in energy per coulomb between those two plates, is the potential difference. All right. Which of the following equations describes E2 in terms of E1? How many people actually found the value of E1, found the value of E2, and then divided them? How many people did that? Good. Good. How many people did like a variable value changing type thing, which is what I did here? Okay, that's the way I'm going to do it. But if you calculated the actual value of the electric field twice and then divided them, that is just as good in this case here. I'm going to say my original field, which, okay, we'll say my original field is E1 is equal to delta V over delta D. Okay, I don't know what its value is. That's okay. I'm going to say my second field, or my new field, after I make my changes to it, is, well, I'm going to make it 1/2 of delta V, because it's 6 volts instead of 12 volts. And my distance between the plates is going to be 3 times delta D, because it's 3 centimeters instead of 1 centimeter. Does that make sense? Those of you who calculated the value of the field, is that okay? 1/2 divided by 3 is 1/6. And delta V over delta D is my original field. So it becomes 1/6 of E1, 1/6 of my original field. You would have absolutely got the same answer if you calculated the electric field for number 1, the electric field for number 2, and then simply divided the two of them. All right, number 4. This is the good question here. We got two charges here. One is plus Q, and the other is negative 16Q, and then we've got 4 points labeled all around those here. On the line joining the two charges, the electric field will be 0 at point what? Well, this is a positive charge. A is a positive charge. So it produces, let's look at all 4 of these points. Okay? Let's label this one my blue one. Let's label this one my green one. Okay, and let's label the electric field caused by blue and caused by green at all 4 of these points here. Okay, the electric field at point 1 caused by blue is this way. It's away from the positive, agree? The electric field caused by 2, or caused at 2 by the blue one is this way. The electric field caused by the blue one here is this way. Agree? Away from the positive? Why did I draw that a little bit shorter than the electric field at number 2? It's further away, so the value of it's going to be smaller, right? And the electric field caused by the blue one over here is even smaller. It's even smaller, but it's still to the right, away from the positive charge. Do we agree with that? Okay, now let's take a look at the green one. The green one causes an electric field at point 4 this way. Agree with that? It's toward the negative producer, and it's really, really big. It's a lot bigger than the blue one was at that point. How come?
16 times Q.
Yeah, the charge is 16 times the value of the other charge, and it's a lot closer. So really, it probably should be even bigger than that, right? But clearly, we can see that they're not equal to each other, so they don't cancel out. And if they don't cancel out, then the electric field will not be 0. Here we would say the electric field is to the right and pretty big. They don't cancel out. Here it's to the right toward the negative producer and a little bit smaller because it's further away. Right? They still don't cancel out. The answer is going to have to be position 1, right? But if we look at position 1, the electric field caused by B is smaller than any of those other ones because it's further away. But it's still to the right. It's still toward a negative producer. So which one, 1, 2, 3, or 4, is the net electric field going to be 0 at?
1.
It's going to be at position 1, right? The only one possible. Numeric response number 1. This one is a little bit to it, actually. I thought it was more straightforward than it is, but it's not bad. 2 metal plates, 1.5 centimeters apart. Here's the potential difference. What's the electric force on an alpha particle? For this one, we're going to use both of the equations that we're allowed to use for uniform fields. E is equal to delta V over delta D. And that's going to give us a value of, when I find my page here, 16666.67 volts per meter. Make sure that you make 1.5 centimeters meters, right? There's my electric field. And now the other equation that I'm allowed to use, E is equal to F over Q, the experiencer equation. So F ends up being equal to Q times E. Make sure you use the charge of the alpha particle, not the charge of an electron, and the 16666.67. When we multiply those together, we end up getting A for number 5, 5.3 times 10 to the negative 15 newtons. Yep.
I just separated the two equations from each other, so like.
Yeah. Yeah, no, absolutely you can do that. You can set those two equations equal to each other. Really, that's what I did here, but I just did it in 2 steps. You did it in 1 step, okay? So if you say this field is 1.6 times 10 to the whatever, and then you say 1.6 times 10 to the whatever is equal to F over Q, which is basically what I did, then again, I'm just doing it in 2 steps instead of 1. Set them equal to each other right off the top. That's fine. Probably saves you about 10 seconds of work as well. Good. Next question. Oh, we got a graph here. A new graph that we've never seen before. V versus D. Now, it does say potential difference. The old notation that they used to use on the data sheet for potential difference was V, and now they use delta V for potential difference, which is better, okay, because it's potential difference, which infers a change, right, which means we should have a delta there, right? Now, the one problem with that is they do call it potential difference here, but the one problem is that they put the symbol on the y-axis as V, and that's an old notation. The new notation that we use is delta V for that. All right, so it's actually delta V. Plate separation we now call delta D, not D. Right? Agreed? Okay, so what do we want to find here in this question? The rate of change of potential difference with respect to the plate separation. What does that mean? The rate of change of the y-axis versus the x-axis. It's the slope, right? It's the slope. That's it. And the slope of that, you could punch your numbers into a calculator, take 2 points on this graph and punch it into a calculator, or you know what? You could just take 2 data points and do rise over run fairly easily. This looks like about 21. 21 times 10 to the negative 2. Subtract 0 over 10 times 10 to the minus 3. Subtract 0. And when I do that, I end up getting, I think I get 21. 21. What would the units be for that, by the way? 21 what? 21 y-axis over x-axis, 21 volts per meter. That answers 2 questions for us. D for number 6, 21, and volts per meter for number 7. Number 8. I like this one. First time you've had to do this yourself, I think. The physical quantity that the slope represents. Okay, we go through that process that we've gone through in a couple labs now. We say y is equal to mx plus b because it's a straight line graph, right? The y-axis is delta v. M is the slope. The x-axis is delta d. Is it okay to x out the y-intercept here? Yeah, like look, it looks like it's going through the origin, right? 0, 0, so we'll x out that. What equation do we have on our data sheet or that we can derive that has delta v and delta d in it? It's the one we learned yesterday, right? E is equal to delta v over delta d. Rearrange that to solve for delta v, I get electric field times distance between the plates, right? Cross off things that appear in both. What am I left with? So what's the answer to that question? The physical quantity that the slope represents is the electric field strength, right? The answer would be C, the electric field strength. How many people got that one? Good. Good. You guys are You guys are getting there. Figuring things out. And finally, number 9, the electric field strength that is just sufficient to suspend a proton in Earth's gravitational field near the Earth's surface is what? What does that word suspend mean? What's another word that if we were to add an entry to our physics thesaurus, what's another word that could mean the same thing as suspend? Anyone? Equal forces, okay. Yep. No net force, balanced forces, equilibrium, okay. If it's suspended, then forces must balance. So we're going to say, well, the electric force equals the gravitational force. Don't ever set the fields equal to each other. Never set two different fields equal to each other. Never. Forces, on the other hand, can be equal to each other. Fields, never. The electric force is Q times E. That comes from the experiencer equation, right? E is equal to F over Q, rearranged, equals M times G. We solve for E. We get mg over q. Okay, we've got the mass of a proton, we've got the charge of a proton, we've got gravity 9.81. We end up getting d 1.02 times 10 to the negative 7 newtons per coulomb. How many people got that one right?